Я могу прямо начинать сейчас, да? Сейчас я проверю еще, как ходит туда-сюда. Слайд ходит отлично. Спасибо большое. Начинаем. Спасибо. Поехали. Hello, ladies and gentlemen. Good afternoon. Yes. Today's lecture is devoted to immunity against severe acquired respiratory syndrome, coronavirus infection type 2, SARS-CoV-2, or COVID-19. Immunity against coronavirus and against COVID-19. In this slide, first slide, you see in the upper part of the slide how coronaviruses enter to the alveoli in the lungs. After the coronaviruses infect human cells, many inflammatory signals are generated. These signals produced by endothelial cells, epithelial cells, dendritic cells, macrophages, monocytes. Involvement of the antigen-presenting cells that you see here is very high. Monocyte hyperactivation causes, in the negative cases, in patients with a severe form of the disease, state that is named cytokine storm. Cytokine storm is a severe disbalance between pro-inflammatory cytokines that stimulate development of inflammatory reactions and anti-inflammatory cytokines that try to control effects of the pro-inflammatory cytokines. But in the condition of cytokine storm, disbalance with a very too high concentration of pro-inflammatory cytokines cause syndrome of hyperinflammation, with the damaging of the human tissues. First of all, of tissues of lungs, intestinal tract, and many other organs. Result of the uncontrolled cytokine storm is development of the ARDC syndrome. This is a so-called acute respiratory distress syndrome. That is a life-threatening condition where the lungs cannot provide the body's vital organs with enough oxygen. In these conditions, multi-organ failure is developed, and on the background of hyperinflammatory syndrome, patient may die. Brief information about virus. SARS-CoV-2 virus is an envelope virus, spherical in size, with a diameter from 50 to 200 nanometers. This virus contains single-stranded positive sense RNA. Size of this coronavirus RNA is one of the highest sized among all the RNA viruses. Genome of the coronavirus consists of 13 open reading frames. You see this in the lower part of the slide, that code for many structural and non-structural proteins. The most important protein, if you pay attention to the vaccines, use of vaccines and development of vaccines, with this most important antigen of this virus is named S protein or spike protein. This protein shown in this slide is a large green molecule with a lollipop structure with a very large peripheral part. This is a attachment protein of the coronavirus and major coronavirus antigen that must occur in the vaccine. The smaller is the size Protein of this virus also integrated to the lipid envelope is named membrane protein or M protein. Here is shown as the spindle-shaped yellow structure. The third protein, shown as a very, very thin green rod, this is an envelope protein E. E means envelope. RNA of the virus is surrounded intimately by nucleocapsid or N protein. This is internal protein that is here, and what spiral symmetry of the RNA depends on the structure of the interaction of different molecules of nucleic acid. At least two virus proteins among these four, membrane protein M and nucleic acid protein, are considered the inhibitors of interference of the first type, interferon alpha and interferon beta. Spike protein responsible for S protein for attachment of the virus to the host cell, and envelope protein is responsible for lysis of the infected host cell. There have been three pandemics of the coronavirus infection in the 21st century. Two have been described before 1919 year. First appearance of the coronavirus and coronavirus outbreaks developed to the pandemic was in the early 20th years of the century, in the beginning of the century. This first pandemic was caused by SARS-CoV without numeration, and infected this virus about 8,000 people. About 800 was killed, and mortality rate of this first pandemic was 10%. Duration of the first pandemic was short, less than 1 year. 7.5 months was the duration of this first outbreak of the virus in our planet in this century. Second attempt of the coronavirus to cause widespread human epidemic and pandemic was made by so-called MERS, Middle East Respiratory Syndrome virus. This virus first appeared in the human population in 2012 year, about 10 years after the first coronavirus pandemic in the 21st century. MERS virus didn't disappear and randomly causes disease in humans until now. About 2,300 people were infected during this time, the last 10 years. Mortality rate was very high, 35%, and it means that this virus could kill about 900 people during the 10-year period of the circulation among people and animals. Camels are considered among animals as the spreaders of this disease for humans. And a novel SARS-CoV-2 by now infects more than third pandemic. This SARS-CoV-2 virus infects about 527 million people, more than 500 million. In this third pandemic, the virus could kill more than 6.28 million people. The leader, the death is the United States, where more than 1 million people were killed by the coronavirus during the last 2 years. SARS-CoV-1 causes an infectious disease called COVID-19. COVID-19, this is an abbreviation meaning disease. SARS-CoV-2, this is an abbreviation characterizing causative agent of the disease, the virus. Most people infected with the COVID-19 virus will experience mild to moderate respiratory illness. It means majority of people demonstrate asymptomatic or mild disease. But some people develop very severe disease and die. They are older people, some children, and those with underlying medical problems like cardiovascular diseases, diabetes mellitus, chronic respiratory disease, different chronic respiratory diseases, and cancers. More likely and more likely to develop serious illness, these people with the chance to die. Pay attention to this slide demonstrating different periods and events that the disease developed. First of all, SARS-CoV-2 virus mostly spreads via inhalation, the airborne disease, or foodborne disease from infected skin of hands also, but mostly this is respiratory disease. SARS-CoV-2 virus binds to cells that have receptor for this virus. Is named angiotensin converting enzyme type 2. Angiotensin converting enzyme, ACE2. Angiotensin converting enzyme. More receptor of this type of the cell, more chances of the cell to be infected by SARS-CoV-2. So, SARS virus binds to the angiotensin converting enzyme in respiratory system in lungs and gastrointestinal system. In these organs, virus enters to the cells, causes virus replication in the epithelial cells, endothelial cells, and in different categories of the phagocytes. First of all, macrophages, dendritic cells, endothelial cells. No, endothelial cells, I told about this. Antigen-presenting cells, macrophages, dendritic cells, monocytes, they engulf virus particles or virus-infected cells, process virus antigens, and present virus antigens in the complex to MHC2 molecules. During this process, cells, antigen-presenting cells, first of all, and other infected cells produce first-line cytokines. These cytokines are, many of them are pro-inflammatory cytokines and may participate in the development of the event named the cytokine storm. Cytokine storm, this is a disbalance of the cytokine production that may cause hyperinflammation in tissues, with the damaging of tissues, and with the death. After presentation of antigen, first of all, antigens are presented to the T cells, to the T helper and T killer cells. CD4 T helper cells also play a role in the source of many pro-inflammatory cytokines. And first of all, T helpers type 1 and T helpers type 17. Interferon gamma produced by helpers type 1 and cytokines of the T helpers 17, for example, interleukin 17 alpha and other, interleukin 21, then also participate in the development of cytokine storm. CD8 T cells react to the virus-infected cells that present virus antigens in the complex with MHC1 protein. In these conditions, T cells and natural killer cells attack the virus-infected cells, damage cells, and also, when activated, produce interferon gamma that additionally enhance the cytokine storm. When saying about antibody synthesis, here to say that T helper cells involved in this synthesis are Th2 cells, T helpers type 2. They're also produced in the patients in the large amounts. Th2 cells stimulate by the cytokines B lymphocytes that have specific immunoglobulin receptors to the antigens of the coronavirus. B cells stimulated by interleukin 4 and interleukin 5 of the T helper cells, T helper type 2 cells, replicate, and their descendants mostly are transformed to the plasma cell that produce antibody of different classes. First of all, antibody immunoglobulin G. Some of these B cells are transformed to the memory cells. So, in the upper right part of this slide, you see list of the cytokines. Level of them are elevated during the cytokine storm associated with the coronavirus infection. But this uncontrolled release of the huge amount of cytokines can be described as the cytokine release syndrome. Cytokine release syndrome that is analog of the cytokine storm. In the cytokine release syndrome and cytokine storm, the following cytokines are increased in their concentration. They are, first of all, interleukin 1, among the interleukin 1 beta and interleukin 1 alpha, interleukin 2, interleukin 6, interleukin 7, interleukin 8, interleukin 17A, the major cytokine synthesized by T helper type 17. Interferons of different types. First of all, interferon gamma produced by T helper type 1 and activated cytotoxic T lymphocytes and natural killer cells. Also, granulocyte macrophage colony stimulating factor. Interferon gamma induced protein 10. Interferon gamma produced protein 10. Monocyte hematocrit protein 1, MCP1. The next subset, macrophage inflammatory protein 1 alpha, MIP1 alpha. Interferon alpha, C-reactive protein, lactate dehydrogenase, ferritin, D-dimer. This is not the complete list of all the cytokines. Level of that is increased and may cause damaging of the tissues and negative results, including fatal results. But what this list that you see here demonstrate most maybe frequent increasing the amount of cytokines frequently. In the any virus infection and including coronavirus infection, first stage in the interaction of the virus to the host cell is the attachment. Angiotensin converting enzyme of the cells attaches to the S protein, spike protein of the coronavirus. But only attachment of the angiotensin converting enzyme receptor to the surface virus protein is not enough to help virus to invade the cell. A second membrane protein that is named transmembrane protease serine type 2, this TMPRSS2, I will repeat, it means transmembrane protease serine type 2, shown red here. This enzyme, after binding of the S protein to the angiotensin converting enzyme, has to cleave S protein of the coronavirus with formation of two resultant proteins, S1 protein or subunit and S2 subunit, produced after cleavage of the spike protein by this transmembrane serine protease. As a result, when on the surface of virus appears S1 protein, virus becomes capable of the attaching intimately to the cell with the fusion of the virus lipids to the lipids of the plasma membrane. And after that, virus may enter to the human body by the fusing. Also, these viruses may be endocytosed and may enter to the human cell by the endocytosis. So, the surface S protein of the virus binds with the receptor of the angiotensin converting enzyme. Significant cleavage event of the S protein takes place by proteolytic enzyme transmembrane serine protease type 2. It results in the fusion of and release of the viral RNA to the cytoplasm of human cell. Also, endocytosis may be used by this virus to enter to the human cell. What is happening in the human cell? But here in this slide and 2 or 3 slides after that, you will see cytoplasm of cell with a gray-blue area surrounded by plasma membrane. Plasma membrane shown here is the pointed line. So virus enters to the human cell. You see this after cleavage of the spike protein, S protein to S1 and S2 portions. This changing of the S protein help virus to be endocytosed or fused to the membrane of the cell. Both these processes are finished by release of the virus single-strand positive sense RNA to the cytoplasm or inside of the endosomes of the virus. Cellular pattern recognizing receptors that recognize pathogenesis-shaped molecular patterns are with these receptors. Group of talk-like receptors, they are exposed to the space of the endosomes. These toll-like receptors recognize single-stranded virus RNA as a pump and generate signal of the activation of the virus-infected cell. How? Toll-like receptor type 3, type 7, type 8, and type 9. What's this receptor? Exposed to the space of the endosome, recognize double sense RNA. After that, these receptors generate the activation of the signaling pathway and transfer signal of the activation to the adapter protein. For example, with this MeD protein, molecules of the virus RNA that appear in the cytosol, not in the endosome, but cytosol. They contact to the RNA sensors. These sensors are also pattern recognizing receptors. Sensors of the RIG1 type and MDA5 type. These sensors, RNA sensors, RIG1 and MDA5, they, after contact with the virus RNA, activate MAFS protein that serves as the adapter protein, activating nuclear factors. Nuclear factors that activating in the process of the occurring and activation of the signaling pathway. With these nuclear factors are NF-κB, nuclear factor kappa B, IRF7 and RF3. After activation of this nuclear factor, signal is transmitted to the nucleus, that's not shown here. What has happened when adapter protein is activated? This is a MeD88 from toll-like receptors, RIG1, MDA5. With RIG1 and MDA5 activate mitochondrial antivirus signaling protein, MAFS, mitochondrial antivirus signaling protein. This protein serves as the adapter protein that transfers signal to the next line of the protein that serve as the parts of the signaling pathway. MAFS transfer signal to the IRF7 and IRF3. For example, how it translate? Interferon regulatory factor 3. IRF3 is interferon regulatory factor type 3. IRF7, this is interferon regulatory factor 7. But these interferon factors, when activated, becomes transformed to the substance that is encoded by ISRE37. No, they are stimulated IRF3 and IRF3 because you see the same indices, and these transcriptional factors bind to the genes that code for interferons and activate expression of these genes. It means transcription of these genes. After transcription, translation is happen, and cells start to produce interferon of the first type, namely interferon alpha and interferon beta. Other signaling pathway that includes toll-like receptors that activate MeD88 adapter protein. After that, transfer the signal to the nuclear factor kappa B. A nuclear factor kappa B, after activation, binds to the fragments of genome that code for pro-inflammatory cytokines, for example, interleukin 6, tumor necrosis factor alpha, and interleukin 1. After that, interleukin 1 protein, when it's synthesized, with the help of the inflammasome, is converted from the pro-cytokine to the matured cytokine that is named interleukin 1 beta, and this cytokine plays a very important role in the development of the cytokine storm. What here, what this dotted line demonstrates events of activation of the so-called inflammasome sensors. No, first of all, what are the inflammasome? This is a complex of the proteins that consist of the sensors. For example, the inflammasome that is shown here has the sensors NLRP3, and via the adapter protein ASC, the signal of the activation of the center is transmitted to the caspase-1. Caspase-1, this is a phosphorylase. This is an enzyme phosphorylating precursor of interleukin-1 beta after synthesis, and transfer of this prointerleukin-1b to the mature interleukin-1b that is released from the cell and activates many cells that after activation develop the inflammatory processes. Inflammasomes may be activated by the different virus proteins directly. It means not only virus RNAs may be detected by the pattern recognizing molecular patterns, but inflammasomes also. And inflammasomes directly react to the virus proteins, for example, to the E coronavirus protein, to the 3A coronavirus protein that appear in the cytoplasm of the cell during the replication of the virus. As a result of inflammasome activation, and the inflammasome stimulate production and maturation of the very powerful pro-inflammatory cytokines. Activation of the interferons that is shown here in the lower part of the slide causes synthesis by the cell of the antivirus proteins that inhibit antivirus proteins that inhibit replication of virus in the cell. Additionally, interferons of the first type activate macrophages, dendritic cells, monocytes, and activate phagocytosis by the cells of the different antigens, including viruses, coronaviruses, including coronavirus-infected cells, fragments of the cells, or complexes of coronaviruses clumped by the antibodies. Blocking the process of the formation and functioning of the signaling pathways, blockade of the producing of interferons, participate in the surviving of viruses in the host cells, and develop a persistence of the virus in the human organism. So, in the pathogenesis coronavirus infection, pathogenesis is based on the functioning of the protective immune mechanisms. Dysfunction of that may cause negative type of the development of the disease. What are these responses? First of all, Th1, T helper T1 immune response. Th1 mediated immune response plays a predominant role in the adaptive immunity against viral infections, many including coronavirus. T cell response majorly depend upon the presence of the antigen presenting mediated cytokine microenvironment. It means T helper type 1 produces interferon gamma and interleukin 2. Interleukin 2 cytokine of the Th1 cell stimulates replication of all the T cells. T killer cells, helper cells, all the types of cells, and even of the B cells. Interferon gamma causes hyperstimulation of the monocytes, macrophages, and many other cells that play a role in the inflammatory process. And interferon gamma is considered as one of the most important causes of the cytokine storm. CD8, cytotoxic cells. CD8 are the killer cells. They are capable of the secreting interferon gamma also, because when they activated, they secrete interferon gamma that facilitates Th1 cellular immune response, facilitating cytokine storm. Exception for that, cytotoxic CD8 cells produce granzymes, perforins that stimulate, that maintain eradication of virus infection, but from other side, facilitate the depletion of some categories of the human cells that may play a role in the development of the lymphopenia. Lymphopenia, this is a very, very dangerous finding in the coronavirus infection. CD4 T helper cells facilitate the overall adaptive response by assessing cytotoxic T cells. Of course, T helper type 1 produce interferon gamma stimulate natural killers and cytotoxic lymphocytes, and CD4 helpers type 17, T helpers type 17, they play important role in the recruitment of the neutrophils and influx of neutrophils in the infected organs, including lungs. This influx of the neutrophils may cause additional damaging of the organs, playing a role in the development of the multi-organ failure. And finally, B cells. B cells producers of some of the anti-inflammatory cytokines, for example, interleukin 4, that counteracts the T helper type 1 immune response, causing lowering of the polarization of naive cells into the T helper type 1. Additionally, interleukin 4, interleukin 5, they stimulate B cells to replicate, to be mature to the plasma cells, and in this way stimulate synthesis of antibodies that are considered very important factors of immunity, helping people to survive. And appearance and presence of the virus blocking immunoglobulins in the organs of the immunized people serve as a guarantee of the preventive development of the severe types of the coronavirus infection. It means the presence of antibodies in the human organisms is essential, cannot guarantee guarantee of the absence of the infection, but can facilitate development of the protective immunity and the levels that is enough to avoid most severe running of this disease. So cytokine storm is a very dangerous situation in humans with the severe development of the disease, is characterized by lymphopenia. Lymphopenia, you know, this is a lowering of the concentration of lymphocytes. And elevated levels of the chemokines and plasma cytokines, such as interleukin 1, interleukin 2, interleukin 6, interleukin 8, interleukin 10, interleukin 17, macrophage stimulating factors, different types of interferons, tumor necrosis factor alpha, and elevated levels of these cytokines are associated with the disease severity and lymphopenia. The presence of lymphopenia and cytokine storm have a significant role in the COVID-19 development. persistence of cytokine storm, it means long-lasting carrying of the storm, stimulates necrosis and apoptosis of different types of T cells. This is responsible for commencing of viral sepsis followed by lung injury induced by inflammation and complications like acute respiratory distress syndrome. We told about this syndrome when human lungs cannot maintain internal organs by the enough oxygen. On this basis, pneumonia or pneumonitis may be developed, respiratory failure, sepsis, shock, organ failure, and potentially death. Severity of COVID-19 is associated with a decrease in the number of B lymphocytes, CD8 T cytotoxic cells, and CD4 T helper cells. For the amount of the natural killer cells, eosinophils, monocytes, and basophils. In this slide, you see scheme of the development of the disease published in one of the scientific publications. So you see SOT shown here in the center of this drawing, and the events, finally number 5 events that are situated on the left or right side of this SOT. First event, lymphopenia, is a hallmark of the COVID-19. Degree of lymphopenia correlates with the disease severity. But in this area that is marked by the number 1, you see not the lymphopenia, but situation that may be developed with the lymphopenia. What do you see here? You see 3 categories of cells that can actively replicate. Actively replicating CD8 killer cells, cytotoxic CD8 lymphocytes that proliferate, produce progeny, and actively produce granzymes, perforins, and secrete interferon gamma and tumor necrosis factor alpha. In this first episode, CD8 cells are not depleted yet. Their concentration is high, but very intensive synthesis of interferon gamma and tumor necrosis factor may, in the future, cause lymphopenia. CD4 cells here on the left part, on the left side from the SOT, these blue cells are also capable of replicating actively, but they also produce the CD4 T helper cells. If they are mostly T helper cells type 1, they produce interferon gamma, tumor necrosis factor alpha, interleukin 2. These cytokines, together with cytokines produced by activated cytotoxic lymphocytes, also serve as the activators of the lymphopenia. And in the lower part of this drawing, you see yellow T regulatory cells. They are CD4 lymphocytes, regulatory lymphocytes, producing anti-inflammatory cytokines, interleukin 10 and transforming growth factor beta. Interleukin 10 is this transforming growth factor beta. They are antagonists of interferon gamma and tumor necrosis factor alpha. Before lymphopenia, these cells also proliferate and play a role in the maintain balance between pro-inflammatory and anti-inflammatory cytokines. But if diseases develop negatively, second episode that started, T cell exhaustion occurs late in the disease. Well, this exhaustion is characterized by the granzyme perforin producing cytotoxic CD8 cell that demonstrate increased number of the receptors, for antigen, T cell receptors, and co-receptors, receptors of the MHC1 and MHC2 plane and other receptors. These cells are undergoing to the exertion. They replicate slowly, but continuously produce interferon gamma. On this background, upregulation of co-stimulatory molecules may propagate the maladaptive immune response. Maladaptive immune response means that on the base of the lymphopenia, not only CD8 cells disappear, are depleted, but CD4 helpers also becomes depleted. And T regulatory cells, what 5, decreased frequency of T regulatory cells is characterized, but not only decreasing of the number, but stop of the synthesis of interleukin 10 and transforming growth factor beta, so anti-inflammatory cytokines. And what we see as the result, we see depleted population of the CD8 killer cells with the increased amount of the receptors on the surface and continuous synthesis of the pro-inflammatory interferon gamma. You see decreased amount of the T helper cells that continuously produce interferon gamma, and dependent on interferon gamma synthesis of the cytokines by other cells. For example, synthesis of interleukin 6 and interleukin 1 by the monocytes and macrophages. And of course, suppressed population of T regulatory cells. What do you see in this right part of the slide? Right to the third. You see lymphopenia. You see low concentration of T killer cells, low concentration of T helper cells, continuous producing of pro-inflammatory cytokines by these cells, and finishing of the synthesis of the anti-inflammatory cytokines by T regulatory cells. But these 3, 4, and 5 episodes of the disease, they explain why in these people, what in the low part of the slide, viral load is increased because these cells can control virus replication. Inflammation is increased because anti-inflammatory cytokines disappear, pro-inflammatory cytokines are continuously synthesized, and of course, as a result, disease severity is increased. Evaluating all these factors, we have to understand that in the beginning of the disease, what in the left part you see recommendations of the therapies to boost T cells and downstream immune responses. It means methods that may help the person in the early period of the infection differ from the recommendations that may help to the patients in the late period of the infection when lymphopenia is highly developed. In the beginning of the infection, when lymphopenia is not developed yet, we have to recommend to administer to the patients interferons type 1 that serve as antivirus substances, neutralizing antibodies are indicated to be administered to bind to the viruses and remove them. And the therapy by the natural killer cells is recommended because natural killer cells may effectively eliminate virus infected cells that stop of exposing on the surface of the MHC1 proteins. They are targets for natural killers. But if disease is developed and we classify this as the late events, when lymphopenia is developed, when profound disbalance of lymphokines is developed, In this situation, recommendations are different. Therapies that inhibit T cell and downstream immune response. They are anti-granulocyte monocyte colony-stimulating factors. Monoclonal antibodies that bind to these factors remove them. Anti-interleukin-6 monoclonal antibodies. Preparations of monoclonal antibodies that bind to the interleukin-6 and prevent its functioning. Anti-interleukin-6 receptor. It means antibodies against receptors to the interleukin-1. Anti-interferon gamma therapies. Monoclonal antibodies that bind to the human interferon gamma neutralizes interferon gamma. And T regulatory cell therapy. It means the last option, this is an attempt to restimulate maturation of the naive T cells to the T regulatory cells. But how this may be done? T cells are isolated from the patient, are cultured artificially outside of the patient's body, and cultured in the presence of the interleukin-10 and transforming growth factor beta of the anti-inflammatory cytokines. In the presence of these anti-inflammatory cytokines, T helper precursor cells, Th0 cells, start to proliferate with the polarization towards the direction of formation of the T regulatory cells. And after a few days of this culturing, a mixture of these newly produced regulatory cells is injected back to the organism of the patient. This slide demonstrates potential mechanisms of SARS-CoV-2 induced immunopathology, because syndrome of the hyperactivation of macrophages, syndrome of the cytokine release and cytokine storm, all these events are illustrations of the immunopathology. Here, four options are shown. What in the left upper part you see of this slide, you see option A, depletion and exhaustion of lymphocytes. 1. Direct killing of the T cells by the coronaviruses that infect these cells. This is the killing of the cells by the virus directly. Second, T cell depletion and exhaustion due to the increased amount of the pro-inflammatory cytokines, tumor necrosis factor, interleukin-6, interleukin-10. These cytokines result of the hyperstimulation of the T cells, and these cytokines, at least some of them, may inhibit replication of T cells. Third episode, virus directly causes damage of organs of the spleen, the lymph nodes, of the liver in some cases. That also may play a role in the lymphopenia, because in these organs, germinating centers are present where T cells replicate after activation. And if this replication is happening in the damaged organs, of course, producing of the new lymphocytes is problematic. And episode 4 demonstrates accumulation of the lactic acid in the tissues where oxidative phosphorylation is inhibited due to the enough oxygen support of the organs. You remember that damage of lungs causes events where oxygen supply of the all the internal organs is lowered, and lactic acid accumulated, and lactic acid accumulation change the pH to the acidic direction with the prevention of the replication of the cells, including T cells. In the upper right part of the slide, you see B object, B drawing. What do you see here? You see that in the background of the lymphopenia, many pathogens require new chance for replication in the patient's organism. You see here bacteria, viruses, protozoa, maybe fungi. In these conditions, when T cell depletion can stop replication of the control of this pathogen, T helper 17 cells are activated, and the activation causes activation and recruitment of the neutrophils, and neutrophil infiltration of the infected tissues. Neutrophil infiltration is directed for the elimination of the pathogens, of the bacteria and fungi, but at the same time, this neutrophil infiltration may make damaging of the organs high. It means neutrophils may play a role as the sources of the reactive oxygen species and hydrolytic enzymes that destroy not only microbes but destroy all tissues also, including tissues containing lymphocytes. Pay attention to the left lower drawing of this scheme. You see cytokine storm. Well, this is a central event in the severe disease. First episode is the cytokine storm. You see that monocyte produces increased amounts of the pro-inflammatory cytokines, for example, of the interleukin-6, granulocyte, macrophage and stimulating factors. This activation of monocytes is facilitated by the T helpers type 1 that produce interferon gamma. It's not shown, but with this stimulating arrow from helper to the monocyte is shaded with interferon gamma. Finally, monocytes produce more and more portions of the pro-inflammatory cytokines. Second, monocyte, when it's hyperactivated, produce the huge amounts not only interleukin-6 and granulocyte monocyte stimulating factor, but interleukin-1 beta. Do you remember in the scheme of the invasion of cell by the virus, you saw that inflammasomes play a role in the maturation of interleukin-1 beta. Production of that is stimulated by the reaction of the toll-like receptors for the virus components, virus nucleic acid, first of all. Interleukin-1 beta is very, very powerful, enhancer of the normal immune response. That is followed by damaging of organs. And finally, T helper type 17. T helper type 17 causes activation and recruitment of the neutrophils, monocytes and macrophages, and infiltration by these inflammatory cells of the infected area that additionally causes damaging of the tissues. The process is regulated by interleukin 17, produced by T helper 17, that after activation of these phagocytotic cells, make them a producer of the increased amounts of interleukin-1, 6, and so on. And finally, drawing number 4, marked by the letter D, in the lower right part of this slide. Antibody-dependent enhancement of the virus infection. Some of the antibodies generated by from B lymphocytes activated by the antigens of the virus are neutralizing. It means they bind to the elements of the S protein of the virus that prevent binding of this virus to the host cells. But some antibodies are not neutralizing that bind to the surface proteins of the virus, but don't neutralize this virus. From other sides, facilitate engulfment of this virus by cells, phagocytotic cells, for example, because antigen antibody complex is shown here, and this complex may cause opsonizing result, facilitating engulfment of the virus by the cell. If antibodies are not neutralizing, this process may be finished by the replication of virus in the cell that phagocytosed virus bounded to the non-neutralizing antibodies. It means non-neutralizing antibodies may make more active process of the infecting of the phagocytotic cells, including monocytes, dendritic cells, macrophages. In this slide, you see pro-inflammatory cytokines that play a role in the development of cytokine storm in the coronavirus infection. They're shown red. And anti-inflammatory cytokines that inhibit activity of the pro-inflammatory cytokines. They are antagonists of the pro-inflammatory cytokines. Pro-inflammatory cytokines are shown red. What in the second graph of this table, you see interferon gamma, red, tumor necrosis factor alpha, tumor necrosis factor beta, produced by T helper type 1. At least one cytokine of T helper type 1 may be considered as an anti-inflammatory. This is interleukin 2. But this is a conditional function. Interleukin 2 is the growth factor for all T cells that are shown here. It means if interleukin 2 stimulates T regulatory cells that produce interleukin 10 transforming growth factor beta that are undoubtedly anti-inflammatory, it means if we will understand that interleukin 2 may stimulate the regulatory cell population. In this case, of course, interleukin 2 will be characterized as the anti-inflammatory. But interleukin 2 also may stimulate replication and maturation of naive cells to the T helper type 1 and T helper type 17 cells. But in this sense, interleukin 2 participate in the development of the disease, of the cytokine storm. So, T helper 17, they play a role in the development of the cytokine storm, producing interleukin 17 alpha, interleukin 17 F, and tumor necrosis factor alpha. Exception for cytokines produced by T helpers, many cytokines, pro-inflammatory at least, are produced by monocytes. For example, pro-inflammatory cytokines produced by monocytes, macrophages, dendritic cells are interleukin 12, interleukin 18, interleukin 1 beta, interleukin 1 alpha is not shown here, but is also important. Interleukin 6. Interleukin 1 alpha is shown. And some other substances, for example, granulocyte macrophage colony stimulating factor. And of course, you see that what green to transforming growth factor beta, interleukin 2. These substances mostly are produced, of course, by the T cells, but what transforming growth factor beta may be actively produced by the fibroblasts forms up and endothelial cells also. It means balance between cytokines stained red and cytokines stained green maintains the healthy state of the patient. If disbalance is directed for the increase of interferon gamma, interleukin 17, and just interleukin 1, 6, in this case, storm would be developed. If this balance will be prevalent interleukin 10 to transforming growth factor beta, in this case, of course, storm would be prevented. Cytokine storm, I mean. To illustrate importance of some pro-inflammatory cytokines, I decided to show effects of the interleukin 1 alpha, pro-inflammatory cytokine produced by macrophages and monocytes. Here you see necrotic cell, virus infected monocyte, for example, that produces precursor of interleukin 1 alpha. This is a pro-interleukin 1 alpha. This molecule is not active yet, but many enzymes of many different cells may activate this pro-interleukin 1 alpha and convert it to the interleukin 1 alpha that is happen when blockade polypeptide is removed from structure of the pro-interleukin 1 alpha. What are the cells and enzymes stimulate activation of interleukin 1 alpha? First of all, cytotoxic T lymphocytes and natural killers on the top angle at the right part of the slide produce granzyme B. Granzyme B, this is serine protease encoded by GZMB gene in humans. This is a enzyme that is crucial for the rapid induction of the target cell apoptosis. You know that granzymes, including granzyme B, this is a typical cytocidal enzyme that is the instrument of the killing of the target cell by cytotoxic T lymphocytes and natural killers. And this granzyme B, stimulates transformation of pro-interleukin 1 to the matured interleukin 1 alpha product. Mast cells produce chimase that also activates interleukin 1 alpha. The neutrophils produce neutrophil enzymes that also activate interleukin 1 alpha. And when this substance is activated, this substance acts to many cells, participating in the development of the cytokine storm. Namely, interleukin 1 alpha, when stimulates endothelial cells, causes synthesis by endothelial cells of the increased amount of interleukin 6 pro-inflammatory cytokine, interleukin 8 pro-inflammatory cytokine, vascular adhesive molecule and intercellular adhesive molecule of the first type, the chemokines and chemoattractants for monocytes that attract them from the vessels to the inflamed area. Coagulants are secreted, many growth factors secreted. Result of this activation of endothelial cells, vasodilation, angiogenesis, producing of new vessels, and leukocyte recruitment. Also, interleukin 1 alpha stimulates B cells for production of antibodies, including anti-coronavirus antibodies. Interleukin 1 alpha stimulates the dendritic cell to increase presentation on the surface of the cells of MHC2 molecules, of the CD86 co-receptors, increasing of the produced by dendritic cells of the interleukin 6, interleukin 8, interleukin 12. They are pro-inflammatory cytokines, you know. Interleukin 1 alpha stimulates B cells for proliferation and differentiation of T cells of different origin. And interleukin 1 alpha stimulates granulocytes for synthesis of leukin 1, interleukin 8, superoxide radicals that destroyed both molecules, viruses, and virus-affected cells engulfed by granulocyte. And with these superoxides may be secreted by granulocytes to the outside, causing damaging of neighboring cells and neighboring tissues that participate in the development of the organ destruction and organ failure. You see how many effects may be stimulated by only one pro-inflammatory cytokine. And now about immunotherapy. I wouldn't explain all the aspects of the therapy of the coronavirus infection, only therapy based on the immune preparations, but now in this lecture. So, in the upper left part of this figure, you see interferon-based immunotherapies. What do you see here? You see administration to the patients of interferon alpha, interferon beta, and interferon lambda. This interferon has been described last in the population of the interferons, and interferon lambda have effects similar to interferon alpha and beta, but slower. You know that this interferon-based immunotherapy is indicated only for the patients with the beginning of the disease and mild event in the disease, because if disease would be very highly developed, these interferons will cause negative effect. Lower than interferon-based immunotherapy, you see quadrant demonstrating cytokine storm management. Cytokine storm management consists of two parts. First is non-specific immunosuppressed agents, such as corticosteroids. Non-specific means that corticosteroids inhibit all the immune responses and all the immune reactions, and not only immune reactions. Corticosteroids down-regulate production of proteins in many types of cells, and of course, cells that play a role in the development of cytokine storm. But pay attention to the preparations shown by the dotted curved line, so-called target therapy. What do you see here? Interleukin 6 blockators, interleukin 1 blockators, interleukin 1 including interleukin 1 alpha that we discussed before, and including interleukin 1b, tumor necrosis factor blockade, interleukin 17 blockade. Interleukin 17, you know, this is a distinctive cytokine of the T helpers type 17. Additionally, interferon gamma blockators and complement blockators. What all these blockators mostly are monoclonal antibodies specific towards these products. These monoclonal antibodies are administered to block and eliminate what cytokines against that are directed from the organs of patients. On the right part of the slide, in the upper right, you see antibody-based immunotherapies. It means administration of preparations that consist of the antivirus antibodies. One of them, plasma therapy. This is administration of plasma of the reconvalescence. IVIG, intravenous immunoglobulin. This is a immunoglobulin that is not taken from the survivors after the disease, but immunoglobulin taken from the routine donors. Some of them may have antibodies neutralizing cytokines precipitated in the immune storm. And finally, monoclonal antibodies directed against, specific to the S protein of the coronavirus that are directed to the neutralized coronaviruses. Lower than what antibody-based immunotherapy, and on the right, concerning cytokine storm management, you see cell therapies. You see different types of cells. Among these cells, you see T cell, what red cell, what the T cells may be administered to the patients. For example, T regulatory cells. Remember, we told about therapy of patients with cytokine storm with the administration of the cell therapy when T regulatory cells are administered to the patient. With the upper part, you see green natural killer cells. Natural killer cells are indicated to be injected to patients with not severe but mild development of the disease in the early stage of the disease. No, some other cells also show, but I wouldn't comment other. I will comment only T regulatory cells administered the late period of the severe disease, and natural killer cells that are recommended to be administered in the beginning of the disease. No, lower you see different things. What immune checkpoint blockade. What immune checkpoint blockade? What we see here, blockaders of the components of the proteins that are components of the signaling pathways. Do you remember signaling pathways? No, for example, what JAK inhibitors, they block pathway of the signaling after binding of the interferon gamma to the interferon receptors of the cell. With JAK, this is a adapter protein. Blockade of the JAK prevents realization of this pathway associated to activity of the interferons. What in the center you see granulocyte, monocyte colony stimulating factors. Here you see a blockade of granulocyte colony stimulating factors to prevent effects of these factors in the process of the disease development. Lower than this line, you see active immunotherapy. Active immunotherapy, but I think that in this case, better to say active immunoprophylaxis. Not so, because you see that parts of these activities are SARS-CoV-2 vaccines and BCG. SARS-CoV-2 vaccines that have been described, and many of that are used now, they're very variable. Among COVID-2 vaccines and anti-COVID-2 vaccines are RNA vaccines, DNA vaccines. DNA experimental RNA is used practically. Viral vaccines, liver attenuated vaccines as the basis of the virus, vector vaccines, spike protein vaccines, subunit vaccines, attenuated and activated viruses, and so on. And the low part miscellaneous immunotherapies, you see absolutely different things. They are not associated to the activity shown in the upper part of the slide. No, for example, anticoagulants. Anticoagulants prevent the thrombosis of the damaged by the virus vessels. And now again about some of these therapies. So, interferon-based immunotherapy that is recommended in the early stage of the infection. Interferon alpha is recommended. Preparations of interferon alpha 1 beta and interferon alpha 2 beta are recommended. They are recombinant products produced as a result of the plan of the gene engineering through the synthesis of the important for humans products. Interferon beta. Interferon beta is also recombinant interferon that is recommended to be used as an inhaled interferon beta 1. Interferons lambda. Until now, 4 types of lambda interferons have been demonstrated, discovered. The interferon lambda 1, interferon lambda 2, interferon lambda 3, and interferon lambda 4. But these first 3 also known as the interleukin 29, interleukin 28 alpha, and interleukin 28 beta. These interferons have the effects similar to the interferon alpha and interferon beta, but they are less effective than alpha interferons and recommended as alpha interferons. Antibody-based therapies. First gray line of the activities. Convalescent plasma, administration convalescent plasma. This is hyperimmune plasma of the people who survived after virus infection. Of course, this plasma contains antivirus antibodies and anti-cytokine antibodies that may help patients to survive the conditions of cytokine storm. Lower, you see gray intermediate line. They are monoclonal antibodies, human monoclonal antibodies neutralizing SARS-CoV-2 because these monoclonal antibodies are specific to S1 subunit of the coronavirus. This is a monoclonal antibody with direct antivirus effect. Polyvalent immunoglobulin or intravenous immunoglobulin. This is an anti-inflammatory product that may cause inhibition of Fc gamma receptors, neutralizing cytokines and antibodies, suppressing the activation of the lymphocytes and inhibiting the function of the complement system. But all these things are inhibited by the polyvalent immunoglobulins because they are pooled immunoglobulins derived from blood of the many healthy donors. This slide is devoted to the management of cytokine storm. Of course, they are not all the known preparations, they are examples of groups of preparations. For example, interleukin-6 blockators. Preparations are tocilizumab and sarilumab. They inhibit the inflammatory pathway induced by interleukin-6 because they block not the interleukin-6 but interleukin-6 receptors of the cells, and in this way prevent contact of interleukin-6 to these receptors. The next monoclonal antibodies, interleukin-1 blockade factors, anakinra and canakinumab. Anakinra, this is recombinant interleukin-1 receptor antagonist. Anakinra, this monoclonal antibody is specific to interleukin-1 receptor, preventing activity of this cytokine because antagonist of the receptor prevents contact of the interleukin-1 to these receptors. Second monoclonal antibody is canakinumab. In the next slide, I will demonstrate you how does act this monoclonal antibody specifically bounded to not the receptor but to the interleukin-1 as itself. Of course, these blockators prevent realization of functions of interleukin-1 and interleukin-6. Third line is interferon gamma blockators. Omapalumab, this is a monoclonal antibody that binds to the human interferon gamma, lowering activity of this interferon in the patients with severe disease. And the lowest line is immunosuppressive agents, non-specific immunosuppressive, because interleukin-6 blockade, interleukin-1 blockade, interferon gamma blockade, all these things are parts of the target therapy. The target is identified. Interleukin-6 for tocilizumab, interleukin-1 for anakinra, and interferon gamma for emapalumab. Corticosteroids, they are non-specific immunosuppressors. These non-specific immunosuppressors inhibit all the immune reactions, but then may cause very negative side effect. They may cause immunosuppression that will help to fungi to hypercolonize human tissues, because immunosuppression caused by corticosteroids may stimulate development of secondary infections. Due to this, corticosteroids are not recommended to be used in the mild or moderate disease, only in case of the severe disease. In this slide, you see how does canakinumab. Canakinumab, this is antibody. Shown here, the antibody consists of the pink or purple heavy chains and gray light chains. This is a human monoclonal antibody specific to the interleukin-1 beta, with these yellow globules are interleukin-1 molecules. As a result, interleukin-1 molecules cannot react to the interleukin-1 receptors. Receptor consists of two transmembrane molecules. Of course, after that, the receptor becomes free and can produce signal for activation of the cell, activation for effects of the interleukin-1 beta. What here is the B part of the drawing, you see normal reaction of interleukin-1 beta with the receptors for the cytokines that stimulate signaling pathway by activation of nuclear factor kappa B that make development of the synthesis, that makes synthesis by this activated cell of the pro-inflammatory cytokines. For example, interleukin-1 beta, via activation of its receptor and corresponding signaling pathway, may stimulate synthesis of interleukin-6 and cyclooxygenases in the patients. Interleukin-6, you know, this is a powerful pro-inflammatory cytokine concerning cyclooxygenase that also is inhibited by the canakinumab. Cyclooxygenase also is named as the prostaglandin endoperoxide synthase, or simply prostaglandin synthase. This enzyme that is responsible for formation of prostaglandins and thromboxanes. Prostaglandins and thromboxanes support the long-lasting inflammatory process, and in this way, cyclooxygenase inhibition is demonstrated by the lowering of the inflammatory processes of internal organs, including lungs. No, you know there are basically three ways to stop coronavirus infection. First, this is allow to people to be infected and generate natural immunity. The most interesting for us, this is a vaccination. Is the methods of the creation of the herd immunity, this immunity of the population, and avoiding symptoms and events associated with the severe disease. Now here you see how restriction methods may help. Now, restriction methods, mask wearing, cleaning of the hands, all you understand. Prevention of the contact of animals, hand-to-hand contact. So all these things are directed for minimizing of the rate of the spreading of disease after contact to one infected person. But here in this drawing, you see in the left part, event where no restriction measures are applied. One person may infect during 5 days about 3 people, during 60 days about 400 people. If in the society restriction methods are supported and are realized, one person infects during 5 days, mostly one person more, and during 30 days only 15 individuals. But you understand that all restrictive measures are not enough to stop development of the disease. What is happened when herd immunity is developed? This is the immunity of people in the population. If herd immunity is absent, it means if sick people stay in red are implemented to the society of sensitive people, they are blue. You understand that finally all of these people would be infected by viral pathogen, and many of them will develop severe disease, some of them will die. If in the society only few percent of the patients are immune, for example, due to vaccination, or survivors after infection, they're shown yellow. The result would be similar to the first, shown in the upper part of the slide. Majority of people will be infected and some will die. But if in the society majority of people are immune, what yellow people in the lower line in this slide, you understand that appearance of the newly infected people wouldn't change the situation dramatically, and majority of people will prevent development of disease and will prevent the risk of the death. Now, how many people should be infected to create the practically fruitful herd immunity? For measles, they're 92%. If percent of immune to measles children would be lower, measles will cause the outbreak, the spread in the society. For COVID-19, this number is less. This is less infectious, in fact. In different periods of the development of pandemic, medical authorities and social authorities told about development of the effective herd immunity if from 70 to 80% of people in society would be immune. Unfortunately, majority of countries, this percentage of the protection is not achieved until now, but many people in the societies are immune, and due to this, only new mutant strains of the coronavirus, what is it, 2020 first and second year, mostly caused increase of the number of the infected people. Vaccines. For the last part of the lecture, I will develop to vaccines. Vaccination is the only way for the herd immunity development. What do you see here? Virus infects human after contact with the angiotensin converting enzyme 2. With the help of the serine protease type 2, virus enters to the cell, liberates its RNA, The basis of this RNA transcription and translation is happen, replication of RNA, new foreign viruses are formed, and these viruses react to the T helper cells. So to that, virus antigens are presented by the dendritic cells and other tissue-presenting cells. T helper cells polarize to the T helpers type 1, 2, 17 or follicular helpers. If they T helpers type 2, they stimulate B cells to synthesis of antibodies. If T helper type 1 to cytotoxic reactions. And we understand that in the development of the cytotoxic, the development of severe form of the disease, prevalence of T helper type 1 cytokines facilitate the severe development of disease, and prevalence of T helper type 2 activities is possible for less severe disease development and the formation of the protective antibody-associated immunity. Till now, variety of the vaccines have been developed and have been described to prevent coronavirus infection. Among them, liver-attenuated vaccines, inactivated vaccines. What in the Russian Federation, Covivac vaccine is an example of the inactivated virus vaccine. Then, vaccines on the base of the nucleic acids, DNA vaccines and RNA vaccines, mostly mRNA vaccines. Then, viral vector vaccines, replicating vectors and non-replicating vectors. Subunit vectors consisting of the S protein of the spike protein of the virus, virus-like particles containing lipid virus-like artificially synthesized balls. To the surface of that, to the member of that is integrated virus S proteins, and peptide vaccines consisting of the fragments of the S protein. I'll characterize briefly three major vaccines produced in the Russian Federation. Covivac. This is a inactivating by beta-protein-lactam virus-based coronavirus infection, coronavirus vaccine. The virus is inactivated under the process of the producing of vaccine, synthesis of vaccine, synthesis of the viruses is based on the culture of the viruses in cell cultures. It makes vaccine rather expensive. Covivac vaccine is supplemented with the allium-based adjuvant. It means this vaccine consists of the dead virus particles associated to the aluminum hydroxide or aluminum phosphate adjuvant. This vaccine was used not very actively, and number of people vaccinated by this vaccine is rather low. Sputnik V. In the contrast, this is a major Russian vaccine, very widely used to prevent coronavirus infection in Russian people and in the citizens of many other countries. Sputnik V, also is named Gam-Covid-Vac, is the adenovirus vector vaccine. The active components are modified replication defective adenoviruses of two different serotypes. They are human serotypes. The serotype 26 for the first component injected firstly, and serotype 5 for the second component that has to be injected 3 weeks later after first injection. These vectors are modified to include the protein S expressing gene of the SARS-CoV-2 virus. Pay attention. This is a two-vector vaccine. Two different injections inoculate to the human body, two different vectors. Both are human adenoviruses, but immunologically they are absolutely different and not related. It means immunity to antigens of the first adenovirus vector component consists of antibodies that don't react to the antigens of the second adenovirus. Both these coronaviruses contain gene coding for S protein of the coronavirus, and these vectors, adenoviruses, are not replicative. They can't replicate in the human body. And the third vaccine, produced in the Russian Federation, Epivac Corona vaccine. This is a subunit, alum-associated vaccine. Epivac Corona relies on artificially chemically synthesized peptide antigen. Antigens are not produced by biological way. They're synthesized by the specialists in the chemical laboratories. It means the vaccine doesn't contain the leaf virus in all the stages of the production of vaccine. Synthetic peptides of the SARS-CoV-2 are conjugated to a carrier protein, and after that, these complexes are adsorbed on the aluminum hydroxide. It means chemically synthesized peptides of this vaccine, of these peptide vaccines, are not the complete antigens, they're haptens, and to make them complete, they must be associated to the protein carrier. But even in this association, they are low immunogens, these synthetic peptides. And to make them active, they are additionally absorbed together with carrier protein to the aluminum hydroxide to make immune response high. But practically, immunization by the Sputnik V guarantee more intensive immune response than Epivac Corona. When said about safety and efficacy of vaccine, we have to say that all the vaccines, known vaccines, are subdivided to the replicating vaccines, the right part, right to this dotted red line, and non-replicative vaccines. They are shown in the left part of this list of the objects. Of course, now in the world, replicative vaccines, they have been developed but are not used practically to immunize some large categories of people. Now, how in this system effectiveness and safety is distributed? Most safe vaccines are shown by the arrow that is shown upper, and the most safe vaccines are nucleic acid vaccines. After the subunit, after some virus-like particles and so on. Effectiveness of the vaccine shown by the second arrow that is situated lower than upper and direct to the absolutely alternative way, alternative side of the slide. It means that theoretically nucleic acid vaccines are low immunogenic. No, they have the lowest immunogenicity. Subunit, some more immunogenicity, but also low, and so on. What about vaccines that we discussed before in the slide before? What most common Russian vaccine is vector vaccine Sputnik V. This is a non-replicative viral vector vaccine. It means this is among non-replicative vaccines comparatively low safety. But concerning effectiveness, this is a most effective type of vaccine among all the non-replicating vaccines. Effective means creating powerful specific immunity, protective from severe forms of the disease. Covivac, this is an activated virus. Theoretically, safety of this virus is higher than safety of the non-replicating viral vector, but effectiveness is lower. Peptide vaccine, Epivac Corona. Peptide vaccine theoretically must be more safe than both Covivac and Sputnik V, but very, very low immunogenic. And due to this, subunit vaccine, Epivac, is supplemented with both carrier protein to convert peptide as the incomplete antigen to complete, and additionally to the aluminum hydroxide. And the most active and minimum effectiveness is typical for nucleic acid vaccines, but they're considered the most safe. Example of this nucleic acid-based vaccine is Pfizer-BioNTech COVID-19 mRNA vaccine. It means messenger RNA vaccine produced by the Pfizer-BioNTech company. This vaccine has the highest use in the Western society in the world. This slide demonstrates that by 2021 year, many absolutely different types of vaccines, not really all known variants, have been studied to choose the most effective and safe vaccines. So here you see vaccines on the basis of the virus, coronavirus, vaccines the basis of the vectors, with green, including non-replicating Sputnik V, nucleic acid vaccines shown blue, mRNA vaccine, Pfizer shown here, protein-based vaccines, including synthetic vaccines with the orange line. But pay attention to the other vaccine that has been studied and is studied until now. This is a BCG, for example. BCG, this is a Bacillus calmette-guerin anti-tuberculosis vaccine against tuberculosis. And this vaccine is very powerful stimulator of the cellular immune response. Of course, antigens of Mycobacterium tuberculosis or Mycobacterium bovis are absolutely different comparing to the antigens of coronavirus. And BCG, as anti-tuberculosis vaccines, can stimulate anti-coronavirus specific immune response. But scientists who studied BCG in this sense said that tuberculosis vaccine, this is a leaf tuberculosis vaccine, very highly powerful antigen, is very strong stimulator of the T-cell immune response, and in this way may play the role of the non-specific immune stimulator that theoretically may, with the society, create the tendency of the people to react strongly to the wild pathogen, for example, coronavirus pathogen, and make something similar to the surrogate immunostimulating effect. But now, of course, BCG vaccine is not practically used with the aim of the stimulation of anti-coronavirus effect. Scientific investigations are continued by this virus, but tuberculosis vaccine is not used practically to prevent coronavirus infection in people. Well, now you see repeating things concerning different types of vaccine. But protein subunit vaccine. Protein subunit vaccine. In the left part, you see T-like particles or rod-shaped particles, orange color. They are protein subunits isolated from the viruses produced in the cell cultures. They are virus spike proteins. By themselves, they are low immunogenic and require proteins to be used as an effective, efficient vaccine. Of course, the second requirement evaluating the low immunogenicity, protein subunit vaccines required multiple doses, minimum 2, but better 3 or 4. In the right part of the slide, you see structure of the antigen converting enzyme 2 of the green color. This is a receptor for virus, and shown lower blue with the red inclusions spike molecule. This is a tertiary structure of the spike protein. With these proteins are considered as the basis of the subunit vaccine, coronavirus vaccine. Virus-like particles. They consist of the empty virus shell consisting of the phospholipids. To that, virus S protein are integrated. This particle has a prevalence lacks genetic material, but it's very difficult to be manufactured. Expensive and practically is not used practically now. Subunit vaccines for viruses, they can be developed only after identification of the protective antigen. And this antigen is identified for the coronavirus as the S antigen. No, these substances may be produced by biochemical means. The biochemical means result of the synthetic artificial synthesis of antigenic determinants that is used in the epivac corona, for example, vaccine. Or antigens may be produced by genetic engineering as a recombinant products. Here you see that subunit vaccines for viruses may be components of this subunit vaccines may be separated in two halves. Conformational epitope recognized by B cells, what they here, and linear epitopes recognized by T cells. In the ideal vaccine, the vaccine antigen must contain from the conformational epitopes that stimulate antibody immune response and linear epitopes that stimulate cellular immune response. Subunit vaccines are poor immunogenic, and due to this, subunit vaccines and peptide vaccines must be supplemented with immunostimulating structures. For example, liposomes. What here you see structure liposome. Liposome, this is a lipid shell. All of them consist of the phospholipids. And to make this liposome vaccine in the liposome structure are integrated various components, various antigens. But to make what this liposome associated to various components more immunogenic, some immunostimulators may be taken as a, for example, QS21. This is a plant saponin from Culae saponaria that had been used in many veterinary vaccines. What Culae saponaria integrated to the liposome structure may make this liposome more active adjuvant. Additional, some second variant of the adjuvant may be monophosphoryllipid A of the non-bacterial origin that also may be integrated to the structure and enhance the immune response against target antigen if this antigen in the form of the S protein or peptide derived from S protein would be integrated to this liposome. Weakened virus concerning coronavirus is considered as enough. Is the vaccine associated to enough risk and attenuated virus vaccines associated to risk. Inactivated not, but inactivated vaccines associated to the killing of the virus by formaldehyde, but from other side, virus nucleic acid and internal proteins, all the components are present that may cause the allergy side effects. Leaf vaccine disadvantages. They may cause disease in immunosuppressed people, disease caused by even vaccine strain. And vaccine may revert to virulent form in the process of the producing, manufacturing. And COVID-19 vaccines may cause the effect on the virus associated with cytokine storm. Very important to administer vaccines to the people who are healthy in the mode of immunization. Viral vector vaccines. Viral vector vaccines may be synthesized on the basis of leaf vector and basis of the non-replicative vector. Non-replicative vector is more harmless. It's not associated to risk of replication. In the contrast, replicating vector may be associated to risk and may cause side effects. Side effects of both these vector vaccines is the anti-vector immunity. Existing anti-vector immunity could blunt the vaccine's effectiveness. Booster shot can be needed. It means when you inject a vector vaccine, you not only stimulate expression of the DNA that is packed inside of this vector and synthesis of the virus protein in the virus vector transfected cell, but the vector is itself causes the antigen against that humans have to develop immune response. It means immune response to the coronavirus and immune response to the adenovirus will concur one to other. And due to this, effectiveness of the anti-coronavirus part of the immunity would be, may be lowered. And very brief characteristic of the the vaccine highly known in the world. First, our Sputnik V, Russian Gamaleya National Research Center for the Epidemiology and Microbiology Russian Federation is a organization developed this vaccine. COVID-19 vaccine consists of the recombinant adenovirus serotype 26, and serotype 5. That these two portions of the vaccine with different adenovirus serotype has to be injected separately. AstraZeneca, Oxford University, and AstraZeneca have developed the chimpanzee adenovirus vector vaccine. In the contrast to the Sputnik human variants of the adenoviruses were taken, isolated from humans. In the AstraZeneca, isolated from chimpanzee. It makes immune response against chimpanzee antigens more effective than against human coronavirus vectors, the human vaccine. And AstraZeneca has only one vector. It means after repeating immunizations, anti-vector immunity also would be increased very intensively, not only anti-coronavirus. Now, how vaccine is can realize its function with various vector virus particle. This is the red component, this is a coronavirus, and purple adenovirus is endocytosed. This vector virus particle is deprotonated. Viral genome enters to the cytosol, proteasomes. So virus protein is synthesized in the proteasomes that are coded for antigenic peptides, and in the endoplasmic reticulum, antigenic peptides of the coronavirus binds to the antigen binding cleft of the MHC2 molecule, and this MHC2 molecule displays this antigen to the T cell. But here you see a demonstration of the presentation of the antigenic peptide in the complex with the MHC class 1 protein. But what in this drawing, I see mistake, because MHC class 1 protein doesn't have two transmembrane polypeptide chains. One chain is transmembrane, a second not. This is a beta-2 microglobulin. Here is drawn structure typical for MHC2. It means if we will imagine that this is a correct demonstration of the presentation of antigen, and this is not this is MHC2. Instead of CD8 cell, you have to place CD4 helper cell. But if MHC1 protein is exposed, in this case, of course, CD8 cytotoxic lymphocytes will recognize this presentation and will be activated. In case of the activation of the immunity by the vector vaccines, both presentations happen. Presentation with MHC1 and MHC2 molecules, both to helper cells and to killer cells. No, I won't comment this slide. This is a vaccine vector particles. This is explain of the what's previous slide that you saw before, but by the words. Nucleic acid vaccines. Nucleic acid vaccines may be DNA, maybe RNA. DNA vaccines are not widely used now because injection of the DNA to the human cells shaded to some difficulties. and human and what this DNA structure as itself may integrate to the human DNA with non-predictable results. What Pfizer-BioNTech vaccine is a typical RNA vaccine that is used very widely in the world. And what is important, mRNA that codes for S1 protein of the coronavirus is packed inside of the lipid shell that protects this vaccine before engulfment to the human cell. This vaccine acts as a virus-like particle, and the lipid protective layer of the shell in the mRNA vaccine fuses to the membrane of the human cell. mRNA is released. After that, it's transported to the ribosomes. On the ribosomes, proteins encoded in this mRNA synthesized, the S proteins, and after that, they are exposed to the neighboring cells on the surface of this transfected virus transfected by the vaccination cell, together with MHC1 and MHC2 molecules, generating both human and cellular immune response. mRNA vaccine is highly active. The producer of this vaccine say that producing is not very expensive, but this mRNA vaccine has one disadvantage. This vaccine needs to be stored at very low temperature, from minus 60 Celsius to minus 80 Celsius. This very low temperature can be maintained by all the medical facilities. And in some cases, the mRNA vaccines were loosened because were stored at the improper high temperature, minus 20, for example. It is not enough. About DNA vaccines. DNA vaccines, this is one of the very intensively developed part of the field of the vaccinology. DNA vaccines considered as the potential vaccines that may be used in the future as the vaccines against HIV, herpes viruses, malaria, and SARS viruses also. DNA vaccines usually consist of the circular plasmid that theoretically may be subdivided to the coding part and the immunostimulating part. Coding part of the plasmid consists of the gene that codes for antigen that we need to need to stimulate immunity. Promoter shown green. Usually this is an animal promoter, some bovine promoter that strongly stimulates expression of the structural gene, and the polydylated terminator that is responsible for detachment of the RNA polymerase from this gene, genetic structure. Genetic structure consists of the promoter, usually of animal origin, gene, usually of the red gene, calling for protective antigen of the parasite, virus, for example, and polydylated terminator. In the left part, you see immunostimulating sequences that may be different in different plasmids. The sequences are responsible for amplification of antibody synthesis by the product that will be synthesized after expression of the gene that is shown red. Immunostimulating sequences may stimulate mitosis in the cells that are transfected by this plasmid. But what are the disadvantages of vaccines? Because these vaccines consist of the biologically active DNA structures that theoretically may be integrated to human genome, these vaccines until now are considered the potentially harmful and continuously have to be examined and studied. But in the nowadays state that are not used to prevent such diseases, coronavirus infection. And the last study demonstrating advantages and disadvantages of vaccines. Viral vectored vaccines. Advantage: stimulation of innate immune response, induction of T and B cell immune response. DNA vaccines, non-infectious, stimulation of the innate immune response, stable, rapid, and scalable production, induction of T and B cell immune responses. Disadvantages for viral vector vaccines. This induction of the anti-vector immunity, cell-based manufacturing of these vaccines. For DNA vaccines, potential integration into human genome, poor immunogenicity with potential integration human genomes. This is an advantage that can be bypassed until now. So disadvantage of DNA vaccine. No, this is the last slide in my presentation. Thank you for your visit to the lecture. I hope that the lecture will help you to pass all the checkpoints and will help you to understand better what is happening in the sphere of the treatment and prevention of the coronavirus infection. Thank you. Goodbye.